Okay, we'll get started. Hello everyone, and welcome to the end of the second week, Theories in Cognitive Science. We are moving from the high level, really abstract stuff down to the more specific stuff. So if you are wondering or fearing that it might stay all high level, have no fear, it's going to get really dense and difficult now. No, I'm just kidding. History of theory. Why do we start with this? Because it's part of the narrative of how we got to be where we are. The ideas that make up the world now, and how things came to be this way. So again, starting with high-level concepts, now we're condensing them into greater and greater chunks about how the brain evolved in the first place, why, and really it's all about creating theories, mental models of reality. And why? Just because it was really useful, really valuable. Fire was a neat trick that could do things that no other element could do that we were aware of. And we built mental models of how to sharpen sticks, sharpen flint, and create fire. And that ability got rewarded and over again until we can create mental models of anything. Let's say that some people have said that human cognition has flown the nest that evolution built for us. Just this really stunning domain general ability to understand gave us this ability to create flight and nuclear fission and to crack the secrets of the universe. It really shouldn't. I mean, when you think about it, nature gave this one ape an ability to represent little bits of reality because it was helped us not get eaten, helped us stay warm. And this domain general ability seemed to be able to represent or build theories of reality in general. Okay, so a little memory test for bonus points. Yeah, let's call that bonus points. A theory, is it the same as a mental model? No? Why not? What's the difference between a mental model and a scientific theory? So what if somebody says, that's just a theory, what would you say?
Like a theory needs to be testable, able to be replicated.
Nice, yeah, so it's got to predict something. It's got to say, well, if we do this, then this outcome should happen. And if it's wrong, then go ahead.
It's based off of research.
Based off of research. We didn't just invent it in our basement. So you look at the comment section online, and you see people have theories, but that's not really scientific theories. So if you can't remember a time when the guy in the comment section and his theories won a Nobel Prize, it's because that never happened. It's people who have created mental models of reality and done research on it, have peer-reviewed it with other people who are able to understand the same work, the same technicality. It's based off evidence. It's based off of prediction and theory, more theory generation and refinement. And so, yeah, so a theory is a really good thing that makes all the difference in terms of whether we can do things. So a lot of people had different theories of flight, and they tested them, and didn't go so well. They tried to fly like a bat, or have giant wooden things that would, not do so well. And learning that, wind actually over a curved airfoil creates lift. That theory, tested again and again, gave us the ability to fly, just by refining our theories. Now, in terms of theories about cognition, this ability that humans have, we've moved from supernatural, sort of magical thinking about, magic or some sort of otherworldly entity to behaviorism. The mind is just stimulus and response mechanisms, gears, that we're just like any other animal. And largely, it's true, but we're an animal plus this ability to do high-level stuff. So these information processing theories, this idea that there's hardware, but the hardware alone isn't good enough to give us any sort of a deep understanding of what's actually going on. We need software understanding, and we need that idea of what's actually flowing through the brain. And if you want to look at the difference between a human that has no software Remember stories of feral creatures, kids who got lost in the woods, over-raised by wolves, over-raised in someone's basement due to psychological or physical neglect. They had pretty much no human-level software, and they were feral. They gnawed at their own hands. They barked like dogs. They were, try to crawl around on all fours. A human without software resembles an animal pretty closely. So the ability for us to move beyond purely animal instincts and hand-to-mouth sort of existence comes with the ability to improve our theories, the ability to improve our software. And we weren't born, none of us, even the human species wasn't born with any sort of deep software. We kind of learned how to run from animals, run towards things we could eat. We learned concepts of what was good to eat, but then eventually thought itself became an object of our own thinking. It was external, and then we started to think about our own thoughts. And people had theories of the mind itself, that it's capable of understanding the universe, that it's competent. Not everyone thought that. Not everybody thought the human mind was competent to understand reality. That we should not look to supernatural theories, because 300,000 years of just perceptual or supernatural ideas didn't get us really above the wheel. But just a few hundred years of taking it upon our own responsibility to direct our own thoughts rationally, to not look to mystical sources for knowledge, to direct our own minds using evidence and reasoning from evidence. And if it's not observable evidence or reasoning from that, we reject it. It doesn't matter how much we love the theory. It doesn't matter how much we love the person who told us. That's not good enough. And so directing our own thoughts using evidence was the game changer of how we got to be this way. And that's how we made advancement in medicine, technology, biology, astronomy, like all the things that we now take for granted. The big puzzle pieces came from this natural way of building theories, of building mental models. And again, I've mentioned that the Greek, the word idea comes from the Greek meaning to see. And so humans were blind to reality and this kind of unknowable universe. And then eventually all the big puzzle pieces got filled in from 1 o'clock there, quantum, atomic, DNA, cells, what we are, what our organs are. The Earth is round and goes around the star, and the stars are other suns. Big puzzle pieces. And again, we're moving to trying to understand cognition itself. So from having rudimentary and sometimes wrong, very often wrong ideas, we move towards this more abstract information processing view of cognition. And we went through dark ages where we still had bigotries, and our culture still had, or many people from our culture still had, really wrong ideas, and they were trying to make the science fit their biases. And so through learning, ability to revise, and that's one of the great virtues of science, is that it doesn't matter how you feel about it, being able to revise theories based on evidence is how things get better and better, and still not perfect. We talked about moving to behaviorist principles, rejecting the idea that there are any such thing as mental entities. Invisible processes in the mind, I can't see that. You open up the brain, it's just a lot of goo. you can't see thoughts or ideas or intention or love or sadness or any of these things. And so behaviorists thought, well, let's deal with humans as if they're just animals. Let's shock animals and reward them. And they found, actually a lot of principles work like this. Humans do work in some ways in terms of reward and punishment, and that does direct our behavior. Tell a kid you can have a cookie or watch an hour of cartoons. You can direct their behavior in a way. Or government saying, we'll give you tax incentives. That's a reward that directs the economics a certain way. So humans are incentive-based, but it's not good enough. It doesn't explain what the human being. It doesn't explain how action works. It doesn't explain how the world is as it is. So revolutions in theories came sort of by accident in some cases. I mean, insulin was created by accident. Sorry, no, not insulin. Penicillin. Penicillin. I think I heard some murmurs there. You're quite right. But you do still have to have the scientific eyes to see and take advantage of. Because if these guys who created this rat maze didn't have the eyes to see and have the scientific education needed, they wouldn't be able to have realized that, we put unrewarded and rewarded rats in a maze. They both learn the maze. That doesn't accord with behaviorist principles of stimulus and response. There might be something more happening, because really these rats shouldn't be learning at all. And here they are. And you do it again and again and again with 100 different rats. You don't reward them, and they all learn the maze. So you need something more, something deeper, information processing. And that sounds really highfalutin. But it also means that there are, information processing means your intentions, your beliefs, your values. And so scientists started off with information processing, and they tried to discover, well, okay, we know that there's some information processing based on these rat experiments and other experiments. There must be something going on in the hardware, and this is one thing we talked about at the end of last class. The hardware, the grid cells, and this was achieved using an empirical method, using testing. So we talked about this Nobel Prize winning discovery that, so the software does connect with the hardware, where you connect a poor little mouse to electrodes, and you see what neurons are firing at a certain time, and it creates this kind of grid pattern where it records where the mouse is going, and it creates this map of where it's been, and it dreams it the evening when it starts to sleep. And they've done tests on humans, and it seems that so they're trying to create this connection between software and hardware. How do the two interact? Okay, they can also be created by this sort of connection, can also be done using rationalist principles. So they tested, and that's how they got to see grid cells. But Chomsky was the guy who used more armchair reasoning, more of a rationalist approach. He sort of deduced what must be so, assuming this empirical evidence. So we talk about the hardware of language acquisition, this really incredible ability for children in just a few years, put in a household with 4 different languages, to just be able to just drink it in and breathe it back out. No accent. When people who are in their 40s or 50s can learn a language for 20 years and have a really heavy accent, they don't have the pronunciation or the ability to slot verbs, nouns, adjectives in the right way. They'll still use their native way. It can sound sort of like Yoda, because their language puts nouns and verbs and adjectives before each other, while English does it the other way around. But every brain has this language acquisition device, this hardware that it just knows what's a noun in any language, what's an adjective, what's a verb. And so the human brain, when it's born, waits. It waits for people to speak to it, and then it starts slotting information. It just somehow knows. In whatever language, that's a noun, that's an adjective, that's a verb, even if it's sign language. It just knows what these things are. And so this language acquisition device is part of an intrinsic mental capacity. And this was Chomsky's big revolution, because he realized that, again, these behaviorist principles are not enough, in that this ability to acquire language comes from some deep hardware, where the hardware recognizes the software. It recognizes the shape of the information. It just somehow knows that's a verb. It just somehow knows, it sort of almost inherently recognizes the information itself. And this language acquisition device came from his argument of the poverty of stimulus, and that there's not enough behaviorist responses and stimulus and response in our environment for us to learn language. It's just not enough. poverty of stimulus. Information required to learn a language is not enough. It's not present in the environment in terms of you don't make kids speak languages just by shocking them or rewarding them with cookies. They just listen. They hear. And it can be really funny what they say back. Sometimes they hear the wrong thing and say the wrong thing. But Chomsky argued that unless they have some sort of deep innate ability to understand grammar, there's no way they could learn even 1/100th as quickly as they do. So children learn phrases without any reinforcement. They learn and discover things without being told, without any sort of pleasure or pain motivation. And so the only thing that explains this is that there is some sort of software and hardware interaction. And so you can't do without this. And that created a paradigm shift. Through history, there are big changes in theories, and cognitive science, our home field, is part of this paradigm shift. There were big paradigm shifts in history where it was a little embarrassing if we lived beforehand. I mean, all of us would have believed that the earth was flat if we were born in a certain time in history. We all would have believed that the brain doesn't actually do anything, that the mind is purely supernatural origin, and that nothing that happens in the brain makes any difference. But now we're knowing better, and so this big change in terms of how cognition works is called a paradigm shift, in that this was created by Thomas Kuhn in his really famous book, The Structure of Scientific Revolutions. So this is a concept that once in a while there's a big shift in our thinking. There are cracks in the old model, and those cracks, the old paradigm, they start to build up, and then the old guards start to try to fix them with band-aids and say, oh, that's a feature, not a bug. And I'll get into the specific in a second, but the more they try to take band-aids over to the old way of thinking, the more people are realizing that we're missing something. This isn't just we need to sort of just create fixes here and there. We need a totally new paradigm. So, for example, the shift from geocentrism to heliocentrism. They really tried for a long time to fix that theory. It's so insulting to think that the Earth is just another planet. I mean, that we're just one more wanderer in the heavens, as they said. It's so absurd. And they try to relate it to their holy book, saying, look, our holy book itself says something, and it didn't really, about the Earth being flat and everything revolving around us. And the shift came realizing the sun was the center, and really a black hole is the center of our galaxy, and really there is no center, but at least the Earth goes around the sun. And in the same sense, theory of mind shifted from behaviorism to cognitivism. So this idea of a paradigm shift is really important because it'll happen again and again. This is how planets move in the sky. Stars move, and they just keep going in one direction. And then these pesky little lights in the sky, these planets that are of course brighter than any other star, will do this, week 1, week 2, week 3, week 4, people will track them, and they'll stop, and they'll go the other way, and they'll keep going. And people said, well, if the Earth goes, if everything goes around the Earth, what the heck is this? It makes no sense. And so they tried to patch up this crack by postulating, these are special heavenly bodies. They have their own little loops within loops. You see, they tried to create more and more complexities to account for things that didn't make sense. And behaviorists were doing something of the same. But this went on for hundreds, if not thousands of years, ever since Ptolemy in ancient Greece. They saw these wanderers and they made up these elaborate excuses for why this actually did make sense in the geocentric model. And so they postulated that, so the Earth is at the center, absolutely. Still, that makes sense, and the stars go a certain way. And these planets Well, the reason why they go across this weird pattern across the sky is they have their own little loops, and they go and they go, and they have more and more loops, and that ta-da, that fixes our problem. And then people were wondering, well, wouldn't it be a lot simpler if maybe something changed? Maybe the way we were wrong about the whole thing. And so this paradigm shift happened in how humans saw the physical world, because here's geocentrism, the old dominant paradigm, was Earth at the center, then everything makes little loops. It doesn't look so good. This is what the Earth and everything looks like if it goes around. And so you got to make these really sloppy, complicated explanations. And so this is a symbol for what happens again and again in history, is that there are theories that are just spectacularly wrong. I mean, they work a little bit. I mean, you can use this to calculate how the planets move. But I mean, there were theories of medicine that were kind of like this, that the body is made of, I mean, they didn't know we were made of cells. It was made out of 4 elements: bile, phlegm, yellow bile, red bile, and blood, I think. And then we got to sort of keep these in balance, and all sickness is caused by the imbalance of these fluids called humors. This was a really big idea for a very long time. Our culture has forgotten it, but even just like 150 years ago, doctors would try to rebalance your humors by sucking out black bile or making you drink mercury. Pregnant women would be drinking mercury because that would then rebalance their humors. Clearly there was something wrong here, and just like geocentrism, we were missing something. We're always missing something. It doesn't matter what period in history you are. There's never been a time when people were born when they weren't missing some giant, big understanding. And there's no reason to think that we're not today living in a time just before some huge leap in understanding. I mean, we could be the one exception in history when we're not missing anything. Probably not. We're probably today living in a time just before some giant, big leap in understanding that in the future kids will be born with, will grow up with it, and they'll pity us poor mortals living before this big understanding. Not sure what it is just yet, but it probably has to do with the nature of intelligence itself that will enable us to get a clearer idea of what's actually happening. And so geocentrism, the idea of medicine, earth, air, fire, and water, this sort of alchemic view of physics changed. And just like geocentrism, instead of the earth at the center, we put the sun at the center. And let's see if this sort of improves things. Yeah, it's actually looking a lot better. Yep, I'm sold. I don't know what you guys are thinking, but I like this a lot more. So, when you put the right premise at the center of your thinking, all the evidence makes a beautiful pattern around it. Whether it's medicine, that cells and microbes cause disease, whether it's physics, that there are atoms and they make up different combinations of chemistry, whether it's the idea that the brain is made out of neurons that process information. We put the right concept at the center, you get a beautiful pattern of understanding that comes out of it. At least a lot of the data makes more sense. There's more to learn, there's always more to learn, but this paradigm shift is one important idea for how we'll continue to make leaps in understanding, and we should be very willing to revise our understandings that we have today, based on our idea that we're probably not living in some very special time in history when there's no more big puzzle pieces to understand. So one of the big changes, again, was that instead of behavior, mental entities are the center of our scientific system in cognitive science. Thoughts, beliefs, intentions, your desires, the things inside of you, those are real, they matter. And that you can either see them as real or you can see them as indispensably useful. So there's 2 ways of thinking about this. You can think of mental entities, intentions, beliefs, ideas. You can think of them as real, your ideas are real, or that they're maybe not sure if they're real, but at least they're so useful that we can't at least do without them. It's a useful tool, a way of thinking. So either way, these invisible mental entities give us an extraordinary predictive power when it comes to human action. Our actions, say cognitivists, are the consequences of our thoughts. Your thoughts matter. Your beliefs matter. Your ideas about your intentions matter. Okay, so Daniel Dennett, you may have heard of him. He's one of the godfathers of cognitive science. He had this idea of saying, okay, well, let's sort of, maybe we can't put concepts and ideas under a microscope. So whether you think they're real or not, you can still see them as indispensably useful. And so this is called the intentional stance. The idea that, don't believe that intentions and beliefs and ideas are real. Okay, you can at least take a stance that acting as if they're real gives us so much predictive power that it just blows away the competition. So he had this sort of thought experiment. Thought experiment is sort of a story that we can use for reasoning purposes. So imagine if aliens were sort of observing humans, those weird little creatures, and they were observing humans and they were trying to investigate why we do things, why we behave the way we do, what's going on in there. So now imagine if they were unaware that we had any thoughts. Imagine if aliens were unaware that humans had any beliefs or theories or anything. How much predictive power would it be if the aliens just tried to map every atom in our bodies to investigate why Billy went to the bank? Just something simple. This animal, Billy, is going to this building. Let's investigate why he's doing that. We have no idea about thoughts and beliefs and intentions, so we're just going to map all the atoms in the body. Is that going to give us any predictive power as to why he's going there, why he might go there again? You see, the atoms were arranged in a certain way that, sort of like clockwork, it pushed his legs and he just kind of, put one foot in front of the other, and that's how he got to the bank. So if you map all the atoms in the body or the whole world, it's still not going to give you as much predictive power as saying, Billy went to the bank because he believed he had money there and he intended to get it out. We can do away with a lot of this mapping of, all the atoms in the body by just taking an intentional stance. You don't have to believe they're real. This idea that intentions are so useful to believe in that it would be more useful than the alien hardware and software from another planet mapping every single atom in the body, which I don't even know that's possible, but it would take petaflops upon petaflops of informational processing, or it can take one sentence of black and white text in a very beautiful slide. Billy went to the bank because he believed. That was his intention. That was his motivating force, this belief. He had money. Money is a symbol for, it's a unit of currency that exists a lot in humans' minds, and he wanted it. He wanted his money. And that was pretty much, that's the intentional stance. You can think of these invisible mental entities as real, or you can think of them as really useful. But either way, you can't really do without them. That's the big paradigm shift, is that whether you're a true believer or whether you just want to think that they're useful to believe in, you can't do without them anymore. It's sort of like believing the earth is flat or thinking there's still earth, air, fire, and water. You're going to be left behind by history. So this was sort of some of the beginnings of what's called computational theory of mind. Now, computation sounds really, abstruse. It sounds really complex, like there's so much to unpack there that you don't really want to dive into it. Well, it's just what we've been talking about, that mind is software, that the hardware of the brain produces the software of the mind. So you can think in abstract terms. So computation as an idea doesn't have to sound scary. It just means information processing in terms of beliefs, intentions, desires as informational patterns in neurons that motivate human action. And so mind, the software, is what the brain does. And so this came about by really recently, actually. Not early, but very recently, these big changes in human thinking happened. It's sort of hard for us to imagine what growing up without computers was like. But pencils, erasers, slide rulers, there was no such thing as information processing devices. So how could we think of our own brain as an information processing device? That would have been really weird. So once we started to build computers, once humans started to build these strange electrical devices that could calculate, they started to think about how, humans and computers kind of do the same things. Computers are doing these things that we thought only living things could do. Information storage, retrieval, problem solving, calculation. That's very strange. There was even previous origins to computational theory of mind that philosophers thought that, reasoning is just kind of like reckoning in terms of adding and subtracting. And actually, the first computer programmer was a woman more in the Victorian era named, and this is true, Ada Lovelace. She proposed that a calculating machine could go beyond math and do thinking operations. So she was credited to be the first computer programmer. In 1833, there was a fellow named Babbage who created this mechanical calculating device called the analytical engine. And so this inspired this woman who was a mathematician and writer to think more about it. She started to realize that these machines could calculate, but they could probably go beyond mathematical calculations to carry out instructions, to do thinking processes on representations themselves. And so she wrote some examples and published them and then sealed her name in history. And so from these mechanical devices where you turn gears and knobs came electrical systems that did sort of the same things. And it seems that this helped us understand human cognition in a way that we never had before. So it was like machines need to sort of hold up a mirror to us so we can sort of look in the mirror and go, that's kind of what we are. So before humans really even understood the body, like back in the time of Descartes, new sort of mechanical devices started to be created, and they started to make these little puppets that had mechanical arms and legs. And philosophers started to look at these mechanical devices that were used as puppets with gears and levers and what looked like tendons. And they're like, the human body is kind of like that. Maybe the body is this kind of mechanical device of sorts. And once they dissected humans, they found tendons that acted like pulley systems. You had muscles that acted like pistons, and you had the bones are rods, and our body sort of is operated very much like a mechanical device. So mechanical devices sort of held up a mirror to humans to say, oh, maybe our bodies aren't this weird, unknowable, supernatural thing. Maybe it's actually just natural causality. Again, this mental move to natural causality. And then in the 1950s, when computers started to come along, these weird little mechanical devices that did processing, it held up a mirror, because they thought, okay, well, maybe the body's mechanical, the mind is special. The mind has some supernatural, invisible entities. And then when computers came along, it held up a mirror to what the mind was. The mind is, maybe there is a natural causal process for how we can do thinking, for how we can do processing of information. So it's almost as if humans need external metaphors to help us understand ourselves. And so this was one of those things that helped us create this paradigm shift, these external metaphors. So here's a fellow. He wrote this paper, which to us seems kind of obvious in retrospect, but he wrote a paper, Can Machines Think? It was a very daring paper. So he was a mathematician in England, computer scientist, code breaker during World War II, and some of those first calculating devices were used to beat the Nazis. But he did a lot of time thinking about the philosophy of thinking, of the fact that I think these machines are showing us something deeper into the nature of thought itself. So this idea of can machines think, which was the title of his paper, got people thinking about maybe human thought itself is a product of causality in this way. So here's a clip from the movie, but it's him, I think, trying to, at the same time, trying to crack some coding, because the war was still on. But he's talking about the future of devices and what that means for the human. It was a very eerie idea, a brain that actually that wasn't biological. What a spooky thing. Of course, we were all born and raised with computers. They're not spooky anymore. Still a little spooky to my grandfather and a lot of people from his generation because they are kind of alien. They're very new on this planet, these electrical brains that do thinking that we used to only think humans and animals could do. So this is the idea that it seems that intelligence itself, this weird principle in the universe, isn't, you don't need biological wetware to run software, to run this thinking phenomenon. It seems that if you understand the principles of intelligence itself, you can put it into non-living matter. If you understand the principles of information processing, you can put it into metal and silicon. You can take it out of the wetware of human neurons and you can put it into the hardware of computer devices. So this is the idea of realizing the same process in more than one substance. And it's not just intelligence that does this. There is a certain category of thing in the universe where you can put the same thing in different substances. So the thing itself exists on a higher, we can say, dimension. And we're going to talk about that in a second, but this is the idea of multiple realizability. You can realize music, for example, in more than one device. It's the same song. Somebody name me a song. Anybody? Any song? Go ahead.
Pictures of an exhibition.
What's that?
I said pictures of an exhibition.
Pictures and exhibition. Okay. You can. Okay. Let's put it on a vinyl. It'll play the same tune, right? If we were to do that, the needle scratching on a record. You can put it in electrical tape if you remember what these are. Electrical tape, totally different hardware. Totally different. Electrical tape. And then you can put it on a flash drive. You can put it on a CD. You can put it on different things. You can put it on a wax cylinder, and that was a real thing. The same thing exists at a higher dimension. The song exists it is what the hardware does. It exists, and it will sound identical no matter what material is being put into it. Sort of like human intelligence. It's this music that plays, and you don't need one type of material. It can be multiply realized. And so this philosophy of mind is part of the idea that this computational theory of mind is the idea that intelligence, cognition, maybe even feelings themselves can run on more than just one type of hardware. So this is a type of functionalism, this idea that the function matters. Not so much the hardware, but what it does. So say if you had a shovel, you could make it out of metal. It's still shovels. You can make the same shovel out of wood. I don't know if it would work as well. You can make it out of really hard plastic. The shovel will still shovel it. It'll still do the same function. Sort of like these different processing devices. What it does is the same. This idea of, and in terms of computational theory of mind, we're defending the idea of functionalism. It's called machine state functionalism. Machine state functionalism, that the machine can do the same function, doesn't matter. It kind of matters what the kind of hardware it is, but you don't need to have living neurons engaging in metabolism, shooting neurochemicals and all kinds of weird things. You can have metal and silicon. You can have, well, some people actually made some type of really simple Turing machine, we're going to get into that, out of Lego pieces and plastic, devices. So this idea of multiple realizability is the idea that things like music, this is substrate, these types of tape and record and the whether it's a wax cylinder or the flash drive, this is substrate. The material is a substrate. And what it does is independent of the substrate. So the music itself is free of the substrate. It's substrate independent. So music is substrate independent. You can run it on many different things. You can have computation that's substrate independent. You can have money that's substrate independent. So what are some types of money that you know of? What type of money you know?
Euros.
Euros. Okay, what's that in? What kind of material? Paper, sure. Plastic. What's another type of money you got?
We have like digital money.
Digital money.
Physical money.
Right. Yeah.
You can even have money in like different forms of digital currency.
That's true. Yeah. Yeah. Exactly. Crypto and Bitcoin. Yeah. You can even you could even say a dead rabbit is or a handful of corn is a style. You can have money in terms of people use seashells. Sorry, I saw a hand up there.
I said oil, gold.
Oil, gold, and so money is a sort of a unit of value that is substrate independent, and that maybe unless you want to eat the core, but people would actually trade it just as a unit of currency itself. Or oil was actually olive oil was something people used to just trade and be like, hey, an olive oil barrel is pretty stable unit of currency, but a $10 bill. Realizing now, a $10 bill yesterday doesn't really buy as much as what it is today. The value of the money is substrate independent, and one of the reasons why our rent is going up and things are costing more, and you can't believe the price of food these days, because money is also multiply realizable. It's also substrate independent, and this is now we're getting. I just wanted to give you many different examples of how music, money, computation, intelligence itself, maybe even feelings and thoughts are could be realized in different machines. So information processing can be kind of like music. They can exist in different mediums, different substrate. Information processing depends on internal representations. We talked about beliefs and ideas and intentions. This means the symbol level. We did talk about, remember the top level of representations, and there's invisible operations, and there's the hardware below. But the symbols, the representations at the top, these are this is what we're going to be getting into a lot more in terms of you can put symbols in more than one thing. You can crochet symbols into a shirt. You can paint it on a sign. It's like the stop sign. You can put it in lights. Symbols are multiply realizable. We know we can put symbols in the human brain because we do. We can put them in computers. We can put them in phones. We can put them in all different types of things. Symbols are super important to this idea of intelligence in that without symbols, it's hard for it to do any processing at all. So examples of internal representations are in the form of thoughts. Our thoughts are not reality. They're symbols of reality. Our beliefs, don't always match reality. Even our feelings about reality, they speak to us as if they're a perfect representation of reality. And that's one of the big tricks it does, but it's not. They're all different ways that information can be encoded into representations. Beliefs, desires, thoughts, all take place on the symbol level, that top level. So this, again and again, I keep getting back to the same principles of cognitive science, in that one of the central hypotheses of cognitive science is that thinking is best understood in terms of representations in the mind, that top level, and computations that operate on those structures. This is super abstract, and if you're like me, I didn't get it the first time. I didn't really get it the second time. But once you get it, And that's why I'm going to explain it again and again. I'm going to show you some cheesy graphics to sort of give you many ways of understanding it. We're going to shorten this because this worked for me. Operations acting on representations. That's short. You can chunk that, and I'm going to give you some ideas of how to explain that. I promise you cheesy pictures. I'm delivering. Operations, think of gears. There are no actual gears in the mind, but this gives you an understanding of what's happening. There are symbols in the mind, symbols of scissors and chemistry beakers and music and all kinds of symbols. They don't move, they don't do anything. The operations, the invisible operations like gears, are what move the symbols around. You know, when you're trying to figure out how to cook eggs in the morning, you have symbols for eggs, you have a symbol for frying pan, you have a symbol for a spatula, symbol for salt, and then the gears, the operations in the mind act on them. I know I need to crack an egg first before I put it in the frying pan. Maybe you're like me, maybe you forgot to do that once or twice. But the operations in the mind move symbols that direct your actions in a way that enables you to cook an omelet or type on your computer right now. You all have symbols of the alphabet, the English alphabet, which I think could be improved a bit. I don't know why we have the letter X, for example, but we do. And these are all symbols in the mind, and you know where they are on the keyboard. And your operations direct your fingers to spell out English letters. And so symbols are being acted on by operations, and that's one metaphor for understanding operations acting representations. That's one. I'm going to give you some more. Any questions about that? Good? Okay. Representations. I'm not really an artist, but I did sort of show you the levels they're at. Show you again and again, operations, gears in the mind. They're invisible, we can't see them, but they move things in our mind. They're moving your fingers right now, or they're moving your ability to encode the information that I'm saying right now. And what I'm speaking to you on is the representational level, the symbol level. Every sound that I'm making isn't a physical symbol, it's a verbal symbol. And you were all raised with the English language, and so you have these symbols in the dictionary in your head. And there are operations bringing in the sound of my voice. It's going through your mental dictionary and pulling and matching the sound of what I'm saying with the meaning of the word itself. So operations are bringing in information. It's searching the sounds that I'm saying in your mental dictionary of the English language that you downloaded when you were a kid. And it's saying, oh, these weird little sounds each have the meaning. And then you are able to then encode it into a different medium. So operations acting on representations. Does this make a little more sense now? See some nodding? Good. Operations acting on representations. If we think of a conveyor belt. So here's one of those new conveyor belts that each little gear in there, these invisible operations, are acting on. We can call these representations in the mind, symbols. And they're each acting, we can barely see them, but we can see them working. These little gears, these operations moving things around. So this is another way of thinking about operations, and each symbol there is a representation, but they move things, they direct them. These things don't act on their own. Operations act on representations. Okay, so I got to crack the egg first, then I got to put it in the pan. Did I turn the stove on? Should I whisk it first, or should I let it cook for a while? I should get to class. What time is it? It's 11:30. I got about 4 minutes. I don't want to probably get there while he's talking. And then let's see. I need to open my computer. Did I remember to turn off the stove after I made my omelet this morning? So these operations in the mind are directing your thinking. We can't see them, they're invisible, but we know they're there because we can see our thoughts moving all the time. The thoughts don't move by themselves. The representations don't move by themselves. It's the idea that we can't see the operations, they're run by the hardware, and the symbols themselves move based on these operations themselves. Now representations can program operations. So for example, when you first learned the English language, you had to download A, B, C, and what each weird little letter was. And so each letter of the alphabet was a symbol that you had to encode into your neurons. And that was pretty hard, which is why they made songs of it, the alphabet song. And then we started to put them together, symbols started to put them together into words. We started to make combinations of these symbols into words themselves. And now we can read words. And we can read hundreds of thousands of words very easily. Now, if you try to look at another language, those symbols, we have no dictionary for them. So if you ever looked at Mandarin, or if you ever looked at hieroglyphics, they're all representations and they all make perfect sense. It's just that we don't have operations that understand what they are, that we don't have a dictionary in our head. And so they pull up a 404 error if we try to look through our library for what they mean. So your ability to encode what I'm saying onto your computer comes from, you do it automatically now. So that's how representations can actually become operations. Doing it over and over, playing piano, you start off with clunky keys, or playing a Wednesday instrument, you sort of understand the representation of where to put your fingers, what sound they make, and then they become so automatic that you can do it in your sleep. You can operate unconsciously and automatically. So consciousness is more correlated with symbols. When you're reading, it starts off as very, very effortful. And the reason why it becomes more automatic is because it gets pushed down. We build up operations. We build up. This correlates with procedural memory, by the way. Declarative memory, symbols. We know what a bike is. Procedural information, operations. These invisible, just kind of gears that operate on their own. Driving itself. You start off with symbols. This is where the key goes. This is where the brake is on the left, the gas is on the right. Not too much gas. Turn it on, look around. Remember learning how to drive in the first place and going for your test? All these symbols you learned verbally. They were very clunky. Your body was jittery. It took effort. It took like the full direction of your consciousness. You had to make sure your awareness was very, very there. But then as you drove, or rode a bike, or whatever, these symbols, you needed them less and less. Why? Because you built up operations that connected with symbols. Yeah, you know just how much gas. Remember first drivers, they don't know how much gas, how much brake, and so they're jerking, and it's pretty dangerous. Well, eventually operations build up, and you smoothly brake, you smoothly accelerate. Have you ever been driving and you were like, I don't think I remember actually driving that last half minute? That's because it was all in the unconscious, more subconscious operations. So this is what happens over and over when you're doing anything. You start off with very effortful conscious symbols. You build up these operations, these gears of the conveyor belt, and then it just kind of acts on its own. You can drive without really even consciously directing where you want to go. And so, as you see what we're doing right now, there's hardware. We don't really talk about it, do we? And when you're interacting with your computer, do you really think about the hardware at all? Or do you just think about software? That's more cognitive science. We're thinking about the software because it matters. When you're interacting with your computer, you never need to know about the hardware. Almost never. There are people for that. Geniuses at the Genius Bar. Or, if you're not a Mac user. You have people who are specifically understand hardware. And there are neuroscientists who specifically understand the hardware of the brain, but you don't need to know it so much yourself to interact with it. We interact with each other's software through verbal symbols. I'm going to send you verbal symbols. You send me verbal symbols. We're going to then act together according to those verbal symbols. Did any of us say, hey, how many neurons were firing at that moment? Tell me about your neurons. Let's see if we can get an MRI and we can see how many neurons were firing. We don't need to deal with the hardware at all. I mean, only when things go wrong. And so the software, these upper levels, are what matter. Okay. I'm gonna pause there for a second. You're gonna like this part 8% less if you're like me. So we talked about abstract principles of intelligence that you can put in different mediums. This is an abstraction that isn't initially fun to learn. If you're like me, I didn't get it immediately. But I'm not doing my job if I don't teach you what a Turing machine is, because it's part of the history of cognitive science, it's part of the history of theory. And so if for the rest of your life you can say, oh, I think I've heard of a Turing machine, I did my job. If you say, I don't totally understand it perfectly, that's fine. You do need to understand it as well as I explain it for the test. But you don't need to get really, really deep into it. This is about more the high-level principles of computation itself. So Turing, this guy who did a lot of work with how cognition can be similar to computation, he created an abstract idea of computation. What's the minimal requirements for the principles of intelligence to move from one thing to another? And so he created this idea of a Turing machine to try to understand the principles of computation and the limits of what can be computed. So he thought, back in 1950, trying to peer into the future is always hard, but he said, may not machines carry out something which ought to be described as thinking, but which is very different from what a man does? This objection is a very strong one, but at least we can say that if, nevertheless, a machine can be constructed to play the imitation game satisfactorily, we need not be troubled by this objection. That's pretty wordy, but the imitation game, just like the movie The Imitation Game, came from the idea that maybe we can build computers well enough that they can fool us. Anybody read the news lately and know about the Google chatbot that fooled a guy so well he claimed it was conscious? Well, this is what we're talking about. We instantiated the principles of computation into a device so well that it was able to play the imitation game and fool people into thinking that it maybe is a conscious being. But, okay, so if we go back to the beginning in terms of how Turing said the basic principles of a computer should be, he said, well, if we have some sort of piece of, the basic principles. If we have some sort of infinite tape, sort of like the reel in an old computer or one of those cassette tapes, if you had a very simple processor and you had some sort of device that read and wrote onto this tape, then in theory, you would have a computer that could compute anything. So, again, you need material, you need some sort of processing device, and you need a read-write head, which is sort of like awareness and action. You need input-output, you need a processor, and you need something to input and output onto. And so this read and write head can write symbols in the tape. He saw it as zeros and ones. It can erase symbols from the tape. It can move one space to the left, one space to the right. If this sounds like basic computational programming, don't worry, we're not going to get any more complex than this. But it's the idea that you need input-output, you need something to actually input and output onto, and you need a simple processor. So these basic principles of intelligence was what Turing hypothesized would be necessary for a computational device. So I'm going to show you, I think, a 45-second video of this guy who actually created an actually working Turing machine, and it works. So you'll see the tape, just the material. Now, this is a symbol for neurons or silicon. This guy, in terms of hardware, this guy said we got tape, we got a processing device, and we have an input-output device. So we see the basic principles of intelligence working. This is the absolute minimum we need. And so seems pretty clunky, but whoops. Okay.
My goal in building this project was to create a machine that embodied the classic look and feel of the machine presented in Turing's 1937 paper on computable numbers. At the heart of the machine is the read-write head. It has the ability to write, read, and erase from the tape. Erasure of the tape is accomplished with a felt-covered cylinder. A small gearhead DC motor rotates the cylinder through a toothed belt and pulley system. To read the characters on the tape, a TSL 1401 line scan camera is used. This camera provides the only source of information the Turing program has for what is on the tape. The tape for the Turing machine is a 1,000-foot roll of white 35mm film leader. Once a program has been loaded, it is started from the console. In this example, the machine is running a simple binary counting program. In this example, the machine is counting from 11 to 16. Because it takes 50 operations to do this, I have sped up the video to save time. When the machine reaches a halt state as defined in the transition tables, the Turing program exits from its loop and control is returned to the console.
Yeah, Turing machine. And so they were trying to figure out what was the minimal amount we needed to do any processing at all. You need hardware, some physical thing to write on. You need something that moves symbols. So symbols in the most minimal form aren't symbols we have in our heads in terms of great complexity. They're just zeros and ones. Okay, so that's pretty minimal. You have a felt tip pen, pretty minimal. You have a little eraser device, pretty minimal. But and the read-write, which sort of is sort of like our conscious awareness that takes in symbols and then directs the machine to write symbols. And so this is why Turing machine was so important in the field of cognitive science, as at least a stopping point in our understanding was Turing was thinking about what are the minimal processes that are multiply realizable. What are the minimal processes that an intelligence phenomena in the universe needs? But okay, so we talked about some basic principles. We talked about multiple realizability. We talked about the Turing test. And so he believed that maybe in 50 years, it'll be possible to create a computer program so good that it can fool us. It can play the imitation game so well that an average interrogator will not have more than a 70% chance of making the right identification. So this original question, can machines think? I believe he thinks is almost a little too meaningless to deserve discussion. Nevertheless, he believes that at the end of the century, in the year 2000, which seemed pretty incredible to a guy in the 1950s. What's that?
I said flying cars.
Yeah, flying cars, exactly. Still waiting for my flying car. Not happening. But we do have, Twitter and whatever else, so, we got that at least. But the year 2000 seemed pretty so incredible that it seemed like at some point we're going to have these incredible devices that will be able to play these imitation games so well that it'll be able to fool us. So here's the Turing test, in that you have a machine and a person in one room, and then you have an interrogator in the other room. And the interrogator asks a question of A and B and attempts to determine, on the basis of the answers, which of the two is a machine. So he tries to guess, is this person I'm talking to a person or are they a machine? And if the machine gets really, really good, this person over here on this very advanced looking computer, we can see, won't be able to tell. Of course, they were doing it through text, they were doing it through voice. And here we have a very 1950s looking computer. If you look at old sci-fi, they couldn't imagine computers getting not boxes, becoming more than, or display screens. But this is the idea that computer software will get so good that it'll imitate people. But they couldn't imagine that maybe it'll actually look like us. It'll actually have a voice too. That was way too fanciful, and he probably would have been laughed out of the field. So text, in terms of how this works. So as well as I can define it, I'm going to play another 2-minute video to show how the Turing test came about. Okay, so that's it. We're going to talk more about the Turing test next time. And have a great weekend, everyone. I'll be here for any questions.